Hi everyone, this is one more problem from electric dipole to choose. In this problem we say that an electric dipole in an electric field E, if you place inside that electric field E, which is shown in over here, so this is actually the direction of the electric field, and this is the two charges. One is positive charge and another is negative charge. They are separated by a distance twice a. Then if that theta is very small, then it's going to be make a oscillation into that electric field, and that oscillation frequency must be f would be 1 over twice pi root over twice q a e divided by I, where a is the separation, which is from center to one charge, is the electric field, and I is the moment of inertia of that system. Fine, let's first find out. We know that if the electric dipole basically we define by that equation, which is right actually that a system of particle in a vector form we express in a form which is basically I equal to 1 to n. It should be the qi, where is qi is the charge, and the ri actually that position vector from a center or a origin, you can say that. For this case we can find out, since I have two charges which is equal magnitude, one is positive another is the negative, and the distance between them actually that twice a, then I can say I will label that distance actually. Let me choose different color. Say I'm going to choose, and this would be my positive. Say the distance from this origin, it is actually that a plus, and distance from that origin to the negative charge is the a minus. I give that subscript a plus and minus because of due to the corresponding positive and the negative charge. Now we can say that over here it would be basically that magnitude of a plus equal to that magnitude of a minus must be equal to that a. If it is that, then I can find out that electric dipole for this system would be basically, I take just magnitude, not a vector. I can say this is the qa for positive charge plus qa for the negative charge. Then that electric dipole p would be basically the twice q into a, right? This would be that electric dipole moment, and the direction of this electric dipole moment would be towards from that. If I draw from, say, I choose that color, it should be from negative to the positive charge. We'll find out that, or it should be towards that direction. It will be towards that direction. We can find out that one. Fine. Let's find out first. Say why it is oscillate first, right? It will be oscillate basically since there are 2 point charges over here. I can say there will be some force on that charge particle. One force would be toward that direction. I can say this would be F plus, force on positive charge. By the same way we can say there will be one more force which would be F minus, force on the negative charge. And we can also find out this positive and that the force magnitude. Basically we know that the force on a charged particle inside a electric field we express by the equation, right, which is actually that force on a charged particle inside a electric field actually the q into e. Using that idea we can say that force on positive charge would be q into e into I hat, right? And force on negative charge would be basically minus Q into IE. If I choose, say this is my positive X, that means I hat, and this is my positive J hat, then this would be plus and minus force. And these two forces basically going to create a torque, because positive charge will be try to align in the direction of the electric field, and the negative charge will be try to align in the opposite direction of the electric field. So that's why it will be try to rotate about this center point, which about this center point. So it will create a torque. We'll see that one. Fine. Now how are we going to find out this torque? Before this torque could be find out using that formula, because we know that the torque could be find out. Say that this is actually the definition of the torque. Torque would be basically that R cross F. So sometimes torque is also known as the twisting force, right? So because it's necessary to rotate a system. Fine. Then for this case we can write this torque in term of plus and minus. Say for I will write down that A plus cross F plus, this is for on positive charge, the torque, plus torque on negative charge. So this is A minus and F minus. Now what is A plus vector and the A minus vector? So look at this. I'm using different color also to space that one. So I'm taking that. So this A plus you can write down. So this is created. This is would be 1, and this is would be another vector, right? Then I can say this vector would be A cos theta I hat, and this one would be that A sin theta Z hat. So that's when I can write down that A plus vector, A plus vector would be A cos theta I hat plus A sin theta J hat. By the same analogy we can find out that A minus would be minus A cos theta I hat minus A sin theta J hat, because A minus is that one. So this is your vertical component and this is would be your horizontal component, or you can say that from this is would be your horizontal component, this would be your vertical component. Fine. Now I'm going to put that value into that torque equation, because I've just time to find out the torque, what would be that formation of this torque. So I can find out this torque would be, so I can write this is the A cos theta I hat plus A sin theta Z hat. This is A plus vector cos F plus, which is Q into E into I hat, plus A minus, there is a minus sign, so that's why I use a curly bracket over here, A, and I also factor out this minus sign, A cos theta I hat plus A sin theta J hat. This is my A minus vector cross F minus, which is the minus Q into E into I hat. Right. Now I have to take the cross product with every term, but from that unitary vector property I know that I cross I basically the 0, I cross I basically the 0, right? But I cross j, basically that k. We'll use that convention over here. In using that convention, I can say this component and this component is going to be cancelled out. In that case, I'll find out this torque would be q a q e sine theta j cross I plus this would be, so this minus minus is going to plus, this is also a q e sine theta j cross I. Then I can write down this would be, this torque is going to be the twice a q into e sine theta into minus k hat. Minus basically is moving to the clockwise direction. Then sorry, this is the vector. Then I can say this torque is basically twice a q, basically that dipole moment, right, which is p. We find out over there, which is that p twice qa. Then I'll find out the p into e sine theta minus k. This minus k, basically the torque is basically in the clockwise direction. Counterclockwise torque is positive and the clockwise torque is negative. That's how you find out this is your electric field E, and that direction of the dipole moment actually towards from negative to the positive charge, we know that, right? So this is actually that p, so this is actually the angle. If you use a right hand rule, then this system will try to rotate towards that direction, which is clockwise. That's why that torque would be the negative over here. So this is, then we can write down this torque in a vector form. This would be p cross e vector, right? So this is it actually in terms of case. Now we can also find out why the torque is going to the maximum. You can find out from this equation. So basically we can find out if, so if I say if theta equal to 0, then the torque is basically the 0, right? If theta equal to 90 degree, then the torque would be basically minus PE, right? Or if you say the magnitude, this minus sign is, you can neglect that, is the maximum torque. In that case, if theta equal 180 degree, then torque is also again going to be the 0. But this is actually the unstable condition. I can draw also this scenario. Say if I draw, this is your electric field, this is the E, then this is your negative charge, this is your positive charge. In that case, the torque is towards, the dipole moment is toward that direction, which is the P, right? So we can say that this is actually that P, they are aligned towards in the same direction. For the second case, say that your electric field is towards that direction. This is the direction of the electric field, but your negative charge and the direction of that dipole moment would be, this is your negative charge, this is your positive charge. Then the dipole moment vector would be towards that direction for the second case, right? So this is actually direction of your P, when angle is basically, this one is the 90 degree. In this case, actually angle is basically that 0 degree. For the third case, say this is would be your direction of your P, which is dipole moment, and your electric field would be towards that direction, right? Which is, in that case, you can say this is your negative charge, this will be a positive charge. In that case, the angle is 180 degree. But this is actually the unstable condition. Why it is unstable condition? You can explain from there. Say when that position of the torque or the position of the electric field and the dipole moment in that way. So this is the P. I can say this is the negative charge and this is the positive charge, right? Then torque will try to rotate that system towards that direction. Electric field will try to align this dipole moment vector towards in the direction of the electric field. Fine. Say when their case is that way, so this is the electric field, but this is your direction of your electric dipole moment, right? So this is, means the situation is that it's come from that situation, but after coming at that position, it has some kinetic energy. Due to that kinetic energy, the system is not going to be stable at that point. It will try to move towards also in that direction. So which is means that after a certain time, that this case would be like that. Say it's going to be the cross. This is will be that position. So that's when it will, due to that kinetic energy, it will try to go in downward direction of this electric field. But when it's crossed, again the electric field will try to align that positive charge. Say this is the positive charge. Again it will try to rotate towards that direction. So that's when again it will move towards that counterclockwise direction. So that's mean it will make an oscillation over there. So we are going to find out that oscillation. Since we find out from this equation that for a very small oscillation, if the theta is very small, we find out the torque, right? Sorry. If theta is very small, then sine theta would be basically the theta. So in that case, you can write down the torque. Tau would be basically minus P E theta, right? And this torque we can also replace by that I is the moment of inertia of the system, I alpha is the angular acceleration, minus PE. We know that from the principle of physics of 1, right? Torque would be basically that I alpha, where alpha is the angular acceleration of the system. Then we can write in one more line. So this angular acceleration we can write down in terms of angular displacement, I d squared theta dt square plus p e theta equal to the 0, or we can write d squared theta divided by dt square plus p e I theta equal to 0. This equation is very much similar to a equation which is derived in the case of simple harmonic motion. We write down that equation basically, if you recall that one, dx square dt square plus omega square x equal to the 0, right? Which is the equation of a system if the system undergoes a simple harmonic motion. This will be the equation of motion. We know that one from the principle of physics, where omega is the angular frequency. Comparing these two equations, we can say that the angular frequency of the system for this dipole would be basically PE divided by I, where I is the moment of inertia of the system, and we can find out that moment of inertia of point mass, right? We know that the moment of inertia for the point mass distribution, actually we can write down a system of particle which is mi ri square, where mi is the mass and r is the distance from rotational point. Then we can say this, if you do that some calculation, you can find out that angular frequency would be P into E by I, or you can write down basically F would be 1 over twice by root over P, actually there we know that, which is twice a Q into E divided by I. So this is actually that would be the frequency of that dipole moment in that electric field, which is they asked to prove. Okay, thank you very much.